Welcome to Snacks Weekly on Data Science. This podcast is all about making data science and machine learning knowledge accessible and less intimidating. Today, we are going to talk about the foundation model. This episode is based on a tech blog titled Foundation Model for Personalized Recommendation, written by the Netflix team. You can find the link in this episode's description. Throughout this episode, we will explore this topic from both the business and data science angles. Now, let's dive in. On the business side, let's take out the problem to be solved. Netflix is one of the largest streaming platforms in the world. It has more than 300 million subscribers across over 190 countries. Every day, members log in on different devices at different times and expect Netflix to instantly surface content that matches their unique preferences. Personalized recommendations are at the very heart of their product experience. Studies show that a large percentage of viewing activities on Netflix comes directly from personalized recommendations. Without them, users would spend far more time browsing the contents, and engagement is likely to drop along the way. Over the years, the company built a series of specialized recommendation models to power different use cases. For example, one model might rank the continue watching role. Another might suggest the next best show for kids. And another might handle trending content. Each of these models worked, but the system as a whole became fragmented. Maintaining dozens of separate models is also resource-intensive, and the insights learned in one model don't always transfer to others. As Netflix's global scale grew, so did the complexity and cost of keeping these systems running. The business motivation behind building up the foundation model was clear. Netflix needed a unified approach that could learn from the massive amount of user interaction data they have, and apply it or transfer such knowledge across all recommendation tasks. By consolidating all available information into one foundation model, Netflix could simplify the engineering efforts, accelerate innovation through iterating on a much smaller model space, and delivering a more consistent and personalized experience to their members. In short, it's trying to keep the core product, which is the recommendation experience, one step ahead. Now that we've understood the business problem to solve, let's shift gear and dive into the technical side to see how the team tackled this challenge. At the center of their solution is a foundation model for recommendations, inspired by advances in large language models. Just as large language models learn patterns from sequences of words, Netflix foundation model learns from sequences of user interactions. This model is built to absorb information across many types of behaviors, serving as a shared knowledge base for generating different kinds of recommendations. To understand how it works, let's break it down into three core components of any machine learning model: the data part, the prediction objective and architecture, and the unique challenges the team encountered along the way. The first challenge is about getting the right data for the foundation model. Every user generates thousands of interactions every day, playing a show, skipping it, rewatching episodes, etc. Feeding all of that directly into a model would be overwhelming. To manage this, the team leverages tokenization, which is a process that compresses and organizes data into meaningful units, or the tokens. Think of it like summarizing a novel. Instead of reading every word, you break it into chapters that capture the essence. In Netflix's case, they count interactions into compact tokens that still preserve important details, such as what was watched, for how long, and in what context. This makes it possible to represent the long histories without overwhelming the model. The analogy to language is deliberate. Just as natural language processing uses tokenization to turn words into units for modeling, Netflix treats defined blocks of interactions as a language of user behavior. Once the user interactions are tokenized, the model still has to process very long sequences of those tokens. Some users have years of history with thousands of events. Traditional transformers, which is the backbone of many large language models, struggle here because attention mechanisms scale poorly with long sequences. To solve this challenge, Netflix experimented with sparse attention mechanisms like low-rank compression, which extend the context window to several hundred events while maintaining computational efficiency. They also adopted sliding window sampling during the training process. Imagine this is like you are reading a book with overlapping windows of text. You might read pages 1 to 5, then 3 to 7, then 5 to 9, each with a few pages of overlapping. This ensures the model sees overlapping portions of history, and giving it broader context without needing to process the entire history at once. The second challenge lies in getting both the prediction objective and the model architecture right for the recommendation tasks. In language models like GPT, every target token is treated with equal weight because the goal is to predict the next word in a sequence. But in Netflix recommendations, not all user interactions carry the same importance. A 5-minute trailer view, for example, should not be valued the same as watching a 2-hour movie. To reflect this importance difference, interactions are weighted differently based on their significance. The other key difference with the traditional large language model is the ultimate goal. A recommendation system is designed to optimize for long-term user satisfaction, not just predict the next click. In contrast, standard large language models typically focus on predicting the immediate next token. To address this gap, Netflix uses a multi-token prediction objective during training, where the model predicts the next n tokens at each step rather than just one. This approach helps the system capture long-term dependencies and avoid short-sighted recommendations. The team also enhances training by introducing auxiliary prediction targets drawn from multiple input fields in addition to predicting the next item ID. For instance, genres derived from a user's past interactions can serve as an auxiliary target. This strategy provides several advantages. It regularizes the model to reduce overfitting on noisy item ID predictions, and it can uncover insights about user interactions and long-term preferences. And also, when modeled hierarchically, this can even improve the accuracy of predicting the next item itself. Beyond data and the prediction objectives, there are other unique challenges in building a recommendation foundation model. One of the unique challenges is about the cold start problem. What do you do with brand new shows or movies that have no viewing history? The team addresses this challenge with a hybrid approach of embeddings. Each piece of content has two representations. One is based on the metadata, like the genre, the cast, or languages. And the other one is based on learned ID embeddings from the user interactions. New shows lean heavily on the metadata embeddings, so they can still be recommended even without those viewing data. Over time, as users watch and interact, the ID embeddings become richer and then take over. To make the system even more robust, the team also uses incremental training of the model. Instead of training models from scratch, new versions inherit knowledge from previous ones. The team warm starts by reusing parameters from older models and initialize new parameters for the new titles. For example, new title embeddings might be initialized by adding slight random noise to existing average embeddings, or by using an averaged combination of similar title embeddings based on metadata. In this way, the system evolves smoothly rather than resetting with every update. The team also observed that their foundation model follows scaling law similar to those seen in large language models. As they increase the size of the model and the amount of training data, performance improves in a predictable way. This gave the team confidence to scale up, knowing that larger models would reliably yield better personalization quality. It also reinforces the idea that recommendations, like language, benefits from massive data and shared representations. Now we've discussed both the business problem and the technical solution. Let's wrap it up. In this episode, we explored how Netflix improves their personalization through foundation models, which learns from massive user histories with tokenization and attention mechanism, and solving the cold start problem with hybrid embeddings. This work shows how principles with large language models can be adopted to improve recommendations at scale. If you like the content of this episode, please subscribe to the channel. Give me a 5-star review and leave a comment. Your feedback is greatly appreciated, and I'll see you next week.